learned about the multivariate hypergeometric distribution in the last video. In this video, we shall learn about some of its properties. Suppose that x1 to xp follow a multivariate hypergeometric with parameters capital N and the sample size little n. You might think that if you put p equal to 1, then you will get univariate hypergeometric distribution. But that's not correct. If p is equal to 1, then there is just a single category, and so x1 will be equal to n. It is just like drawing an SRSW OR from all college students and counting how many of them are human beings. You will just get the sample size back. In fact, the simplest non-trivial case occurs when p is equal to 2. Now this corresponds to our univariate hypergeometric, but that might look odd, as then we have x1 and x2, which looks like bivariate, not univariate. Actually, the x sides always add up to n, so here this x2 is actually n minus x1. Hence, effectively, there is only x1 which indeed follows univariate hypergeometric distribution. Let's use the notation x1 follows hg n n1 n. Here, capital N is the sample size, as the total population size, n1 plus n2. n1 is the size of the category of interest, and little n is the sample size as usual. Next, again consider the general p case. x1 to xp follows hypergeometric, multivariate. Suppose I interchange x1 and x2, leaving all the others in place. What will be the distribution of this permuted random vector? It is easy to see that the ni's will get permuted accordingly. This happens for any permutation of the x size. The permuted random vector again has a multivariate hypergeometric distribution with the ni's permuted accordingly. This is because the labeling of the categories as 1, 2, 3, etc. was arbitrary. If the categories are colors like red, green and blue, I may call red 1, green 2 and blue 3, or red 2, green 3 and blue 1. Just the labels change, nothing else. Trivial as this might sound, it is nevertheless of great use while proving certain results, as we shall see later in a future video. Well, again we have multivariate hypergeometric n1 to np and then this little n. Now what is the marginal distribution of each of the xi's? When we focus our attention on only xi, it is like we have only two categories, category I and all the rest. So we are back in the p equal to 2 case, that is univariate hypergeometry. Now the ith category consists of ni individuals, and all the rest category therefore has n minus ni individuals. The sample size still remains little n and population size remains capital N. Thus the marginal distribution of xi is this. If x1 to xp follows multivariate hypergeometric, then marginally we have seen each xi follows univariate hypergeometric with the corresponding ni. So you can see the expectation should be simply n times ni by n. Even if you do not remember the univariate hypergeometric mean, this is a natural guess. Capital Ni out of capital N individuals in the population are in category I, so the population proportion is Ni by N. We have drawn a simple random sample, so the sample proportion is expected to be the same as the population proportion. So out of little n sampled individuals, little n times Ni by N may be expected to be from category I. So, combining all these things, we have expected value of the entire random vector as, take the n by n common, n1 to np. You may try to prove this by brute force using the PMF as well, but there is a nifty trick using indicator variables that makes the proof much easier. We shall discuss that in the next video. The dispersion matrix of x1 to xp is a p by p matrix with the ith diagonal, which is variance of xi, and for I not equal to j, the ij of diagonal entry is covariance xi and xj. Again, if you remember the variance of univariate hypergeometric, then you know that the variance is this. I know it looks bad and not at all obvious. The covariance is even worse. In fact, so bad that I do not even care to show it. But deriving the expressions is not much difficult once you learn the indicator trick that we shall discuss in the next video. Do not try to memorize this formula. Rather, learn the indicator trick so that you may compute these on the fly if you ever need them later.